Welcome to my lecture on eigenmodes of an optical resonator. The course again still is laser physics, and this is basically kind of like the best lecture we have on this chapter 3 regarding passive optical resonators. So this is a little bit maybe math heavy, but don't worry, we will get there ultimately. And what we will be discovering in this lecture is that we will be discovering a little bit about the structure. So eigenmode structure of our optical resonator. So basically that what kind of longitudinal and transverse modes we may have in our laser configuration, laser cavity. And then finally also we will be going through the piece of mathematics that we can understand how a Gaussian beam is propagating within the laser cavity. So that's extremely useful piece of mathematics to then understand how we could really understand propagation of light within a cavity using ABCD matrix formalism. So many things we will be covering in this lecture, so please pay attention and try to follow me mumbling through the materials. So let's start with a very brief introduction on the topic. So modes in general, or eigenmodes to be more strict about the terminology, these are extremely important, extremely fundamental concept in physics in general. So not just in laser physics, not just in optics, but eigenmodes just pop out in general from the mathematical framework many times when we are dealing with eigenvalue problems, or we can recast our problem mathematically into an eigenvalue problem. From there we automatically have eigenmodes arising. So they are essentially relevant to all problems and situations that can be cast into an eigenvalue problem. And if you Google around or you ask your mathematician friend, you see that eigenvalue problems are everywhere in nature, in engineering sciences, and in our society. So they are extremely important piece of mathematics. And we are now basically relying on these mathematics to kind of understand how a laser resonator behaves. So here we want to understand how and what limits the imposed transverse structure and longitudinal structure of fields within the cavity. So basically how the boundary conditions imposed by the mirrors of the cavity limit what kind of field distributions we may have and what kind of resonant frequencies we may have within our laser resonator. So resonant frequencies, basically, they define the longitudinal modes of the field inside the cavity. So that's one thing. And the second thing is that we can also have transverse eigenmodes of the cavity. So that's basically correspond to different kinds of solutions of the paraxial equation that we will be soon covering. And these transverse eigenmodes, transverse field distributions, they correspond to different kind of laser beams propagating slightly differently. They exhibit the same symmetries as imposed by the cavity configuration. So depending on what kind of cavity you have, you will have a slightly different kind of transverse mode families to deal with. But more on that later, also even with pictures. So what we will do next is that we will need to find a kind of a self-preserving or shape-preserving mode, and that's what we call an eigenmode. And the kind of constraint that we have in our system is that after one round trip, so a cavity length of L is the resonator length, the transverse profile of the electric field repeat itself. So this is the physical requirement that we now require to find what kind of modes can be supported by the laser cavity. So basically, in terminology, we would call that we are seeking for a self-similar solution. Mathematically, what this means is that if you have some kind of transverse field profile denoted with U, and we are just looking at the simple plane and the transverse coordinates are X and Y, Z coordinates is 0, which can just arbitrarily dictate that the Z value equals to 0. We require periodic boundary conditions. So after propagation of one round trip in a standing wave configuration, round trip length corresponds to 2 times the cavity length. This condition must be present. And this basically can be written in a way that we can multiply the original factor with some kind of sigma factor, and we can have a phase factor, but otherwise we must have a self-similar form. So basically, we can have some kind of degradation. For example, the amplitude may decrease, but the actual transverse shape should remain unmodified. And of course, we may have some slight phase deviation, but this is the kind of requirement that we have. So basically, only possible modification to the field is sigma, and the modulo of sigma can also, sigma can also be a complex valued number, so we can have an amplitude. So the amplitude may change, and also we have a kind of additional phase accumulation, and this arises from the factor of 2L cavity length propagation. So this basically means or originates from the phase evolution of the field during propagation of one single round trip. So cavity length of L, 2 times L is the round trip length. And this is the kind of condition that defines our eigenvalue problem for the field inside the cavity. So basically, generally, infinite discrete sets of transverse modes arises. So in principle, we may have a kind of like family of different transverse distributions. We'll label them with A and B. So basically, like kind of family along 2 different orthogonal transverse directions along X and Y. And basically, this also means that we may also have different kind of sigma factors, and these may be forming an infinite series in principle. In practice, it's pretty hard to make a kind of infinitely extended laser cavity. So of course, in practice, these kind of like numbers of transverse modes are limited, but at least in principle, this is how the mathematics would scale up if we would be able to make an infinitely large transverse cavity. Fixing the amplitude UAB, we can just denote that then as a U, we get a one specific transverse mode. That's how the math goes. And B, we can generally have infinite and discrete sets of resonant frequencies, now resulting from the phase shift of 2 pi n. Please, n here is now the kind of like integer per round trips. So this is more on the kind of like a kind of longitudinal modes. So this is what we may have. We may have different kind of frequencies of light per different mode. And it's given by c, speed of light, divided by 2 times L. L is the cavity length times n integer times phi AB. So that's the kind of phase factor associated with a different mode times, divided by 2 pi. And then this phi plus 2kL equals to 2 pi n. So this is how we define the phi factor. Phi parameter. So basically, this is the resonance frequency. And as we can see, the resonance frequency of a given mode now really depends on the mode. So on the transverse mode and also on the longitudinal modes. So this is really how things are being dictated or being defined by the cavity geometry. And here, this phi term giving us the kind of like phase associated with a given transverse mode can be calculated through here, and we can see that they are interlinked also to the longitudinal mode index n. So fixing for a given transverse mode, so fixing A and B, we can calculate that then the given frequency gives rise to a family of longitudinal modes. So this is basically what I want to say here, that this n value gives rise to a different sets of longitudinal modes. So things really get more complicated when we are starting to look at the many resonances that we have, and also of the possibility of having many transverse resonances within our laser cavity. Now looking at the phase condition, so this math we already outlined. What we can say here is that we can see a few points worth noting. So the cavity length L basically defines the longitudinal mode spacing. So this is basically cavity length here, and this kind of like gives us the kind of mode spacing. So basically the cavity length is really important parameter if you want to be looking at how many longitudinal modes might be, for example, lasing. A kind of like rule of thumb here is that if you make a shorter cavity, then you have less longitudinal modes. And sometimes that's nice things, because then you can increase the coherence length, the coherence properties of your laser by reducing the number of longitudinal modes that are lasing. Sometimes you really want to have multiple longitudinal modes lasing, and even in fact lasing in a coherent manner when you want to make, for example, an ultra-fast laser. So of course there are either ups and downs regarding the cavity length. But nevertheless, like it's a parameter that really dictates the longitudinal mode spacing. I think that's the main thing for you to grasp here. Then the transverse mode spacing is really determined by the symmetry of the cavity, and the kind of properties of the transverse modes are really dictated by the symmetry of the cavity. So it's really worthwhile to look into the kind of like what kind of cavity you're actually forming, how the mirrors look like, and how the beam propagates. Are there some kind of asymmetries there, like changing the transverse mode families and so forth. And for all n an integer, in principle, an infinite number of transverse modes exist. So that's in principle what this mathematics we deal so far gives us. But here, of course, we don't say anything about the actual finite size of our transverse cavity. So, of course, in practice, things will be limited. And the question I want to impose to you for the discussions is that now, if we do have a given transverse mode, so for a given A and B values, do we really have an infinite number of longitudinal modes that would exist in the cavity? So this is something I would want to ask from you, and hopefully we can discuss during the upcoming discussions. And now let's go forward, because like this question has been imposed to you already. Okay, let's now look how the transverse modes actually look like. So let's really start solving the functional form of the transverse modes. And how do we start here is that we start with the wave equation. So basically wave equation in a homogeneous medium, we can derive that from the Maxwell's equations, and the wave equation, it's a nabla squared plus k squared times the E field, and that should be equal to 0. So we are in a homogeneous medium, no sources, we are only dealing with a propagation of electric field within the medium. And we assume for simplicity that we only have an x-polarized field propagating primarily along the z direction, so that we can simplify the mathematics. So now we have a field that propagates along the r direction, and mostly it's really along the z direction. And we have basically, in principle, we could have x-polarized field component, we could have y-polarized field component, but basically we are assuming that we only have x-polarized field component so that we can simplify the mathematics. So now, in general, we would be having a mathematics something like this for the general case that we could have both possible polarization components, and in principle, we could have slightly different amplitudes for these, and the propagation might be different. But for simplicity, we are only interested in a one polarization component. We can deal with that, and we can generalize things later if really absolutely necessary. So we just forget the y-polarized component that it could possibly exist. And now we can just simplify math and just write that we are dealing with a amplitude of u that depends on r and depends on the z, the propagation distance. And we take use of the paraxial approximation. So basically we assume that the evolution of the amplitude u is quite weak with respect to the kind of propagation lengths of interest. So basically this is a kind of usual approximation called paraxial approximation that can be used to help out calculating this nabla term here. So we are assuming that the mode does not quickly change upon propagation. The Helmholtz equation that follows basically becomes the paraxial wave equation. So we can write like a previous differential equation in this form. So now by assuming the paraxial approximation to hold, where we do have this like a nabla squared transverse nabla of this form. So we are not really dealing with the longitudinal field evolution here. And these solutions can be readily found, and these solutions into these differential equations are called optical beams. And now the question is that how do we solve this kind of equation? How do we find fundamental solutions to this kind of paraxial equation? And there are really many approaches that can be used to find these ones. And here we just choose one. So I guess maybe this helps out in other pieces of mathematics where you want to be understanding, for example, kind of like tightly focused beams, propagation of Gaussian beams. So at least this approach is kind of very readily generalized into that kind of mathematics. So let's use a angular spectrum representation here to show what kind of solutions can be found for the paraxial equation. So basically what we do here is that we rely on angular spectrum representation. So what that is, more on that of course by Lucas Novotny's and Bert Hecht's book, Principles of Nano-Optics. Excellent textbook in general. I really recommend looking into that for many interesting bits and pieces of physics and optics. And basically this angular spectrum representation mathematically means that we take a 2D Fourier transformation of light. So we describe an arbitrary U amplitude distribution that now is in real space. We describe that in the 2D like Fourier space. So we basically take a Fourier transform of our wave function, optical field, and we write this kind of like a arbitrary amplitude, transverse amplitude using plane waves of sorts in the k-space distribution, in the k-space. So basically we take a Fourier transformation and we describe our arbitrary beam using plane waves. And then this is way to solve the Praxial equation. So basically the k transverse looks like this, and that's basically kind of like placed here. So this is basically just a two-dimensional Fourier transform of this wave function. And this is nice because now we can really substitute this into the previous equation, and we can then calculate the nabla, because for a plane wave things get easy. So we can really write things in a simple manner. So we are then turning the nabla equation into something like this, and here k is the transverse component of the wave vector. And this is a first order ordinary differential equation with respect to z, so we can readily find a solution to that. And the solution is of this form, so it's basically some kind of amplitude at a given plane of z equals 0, and then we have a exponent phase factor given by the exponent I times z times k transverse square divided by 2 times k. So this is basically what we have as a solution to this ordinary differential equation. So basically why we went and used angular spectrum representation is that now we wanted to get rid of the nabla term, and we went into the angular spectrum or angular domain. We took a 2D Fourier transform, and then we were able to just write the nabla terms using k squared terms here, and this is something we can readily like just integrate to find the solution. And now we can substitute things back, and we can really calculate the integral that how does this arbitrary amplitude distribution look like, and now we can plug in this kind of solution into the original Fourier transformation like this. And now we can set for simplicity that at the plane z equals 0, we have unity amplitude for the field, and then we are having this kind of integral, and we note that this is even separable integrals, so we can even write the integrals as two separate integrals like of this form. So now we are in a simple way that this is actually something that looks like a Gaussian integral, and this can almost be readily integrated by using kind of like known values of integrals of Gaussian integrals. So now we are almost there in terms of our derivation. So we are dealing with this kind of integral and the same integral for the y-coordinate, but basically it's of same functional form, so we don't really need to be considering that right now. And this is a Gaussian integral which could be calculated analytically if we would have this condition holding. So if the real part of the iz over 2k would be larger than 0, we would be able to calculate this Gaussian integral. But this doesn't hold, so what we need to do here is that we need to generalize the integral into the complex plane, so we need to replace a z with a complex valued q parameter. So basically we are replacing z, real valued quantity, with something q that depends on the z and is of this form. So we have z minus I z r, where r is known as the Rayleigh range. What follows in the final stages, like sometimes it's extremely useful to describe this q parameter also using the inverse q. So like this will help out you to grasp the final points of this lecture. So sometimes you can also like describe this in this way. And now we have the radius of curvature of the wavefront of the beam here. We have the beam size as a function of z here. We have the refractive index, we have the wavelength of light here. So sometimes this form is actually very useful for calculating propagation of Gaussian beams. But more on that slightly later, just like bear with me. So this ZR is known as the Rayleigh range, and it's given by the refractive index, and now n is really the refractive index, n times pi times W naught. So this is so-called beam waist squared divided by the wavelength of light. And this can also be written in terms of the wave vector amplitude k and the beam waist W naught. And this is known as the Rayleigh range. Final result then gives us the transverse mode profile. So the U looks something like this. So we have the inverse of Q, exponent of I k r squared divided by 2Q. And that's it. So this is now how we can describe a Gaussian beam. And the nice thing here is that we really can describe the evolution of the amplitude, and this is really the kind of electric field evolution with respect to the z. So basically with respect to the propagation within the cavity. So now we can really start plotting how the field is evolving within the cavity when we are able to cast the field into this kind of form. And this is the nice thing here. The physical meaning of this Rayleigh range becomes clear by just looking at the exponent and rationalizing that. So basically we can look at the exponent of the previous field amplitude profile. So we had this exponent term there, and we can write that in this kind of way where the r squared equals to the x squared plus y squared. So basically now this Rayleigh range here helps out to understand how light is being propagating. Here W squared is basically the kind of a beam size or beam width, and that's given with respect to the Rayleigh range. So in a way, this Rayleigh range is a kind of scaling factor or normalizing factor that kind of affects the beam width as a function of z. So basically, if Rayleigh range is large, then the propagation is not as heavily affecting the beam width. But if the Rayleigh range is very small, then of course the beam width is being more quickly changed. Beam waist W naught is the beam size at the z equals 0 plane, and then we have the radius of curvature, so that's basically the wavefront curvature given by z times 1 plus zr, the Rayleigh range divided by z to the power of 2, and this is known as the wavefront curvature. And again here, the kind of physical meaning of the Rayleigh range, we can see that the wavefront curvature r is really being dictated by the size, by the strength of the Rayleigh range. Please note that at the position of the beam waist, where basically the beam width equals to beam naught, the beam W naught, the beam waist, we have a case that the wavefront curvature is infinite. So basically that means that we have a planar wavefront. And please note that that we are saying that we have a planar wavefront really means that we have in principle purely transverse electric field at the beam waist. This is an approximation because we are really assuming here that we have a Paraxel approximation that holds. And basically the next level of approximation would be that the so-called scalar diffraction theory holds. And when these approximations are valid, then the electric field is purely transverse at the beam waist. But that is not really the case in real life when these approximations are really no longer holding well. So for example, if you're focusing your laser beam tightly, you actually do have a non-transverse electric field distributions at your focus. So then you would really need to be doing a little bit better calculation than what we are doing here. So I just wanted to warn you that if ever you need to be dealing with that kind of physics, that kind of mathematics, it's not really a transverse field ultimately anymore at the beam focused, at the beam waist location. And now the kind of math that we encountered for the Rayleigh range, that basically gives us that the beam size, the beam width at the distance of Rayleigh range from the beam waist is basically increased by this factor. So basically the beam size at the Rayleigh range value of propagation length is given by the beam waist squared and the square root of 2. So that's in a way how do we define the Rayleigh range. So another way of saying Rayleigh range is the propagation length after which the irradiance profile of the mode is twice the beam waist. So that's how we define the Rayleigh range. And now, after some straightforward but tedious algebra, we can write the Gaussian beam in its formal form or normal form in a way that the fundamental Gaussian beam looks something like this. So we have this kind of denominator term depending on the Rayleigh range and propagation length and the square root of that, and then we have an exponent where we have these kind of terms there. So this is basically the kind of like final form for the Gaussian beam propagation. And finally, like interesting thing here is that we have this kind of like appearance of an additional phase term, this phi term there. It's known as the GUI phase shift, and it's given by the Argus tangent of the z over zr, the Rayleigh range. So this is basically the kind of final form for the fundamental mode. So these indices here mean that this is the fundamental mode transverse profile, and there's a kind of like this kind of like a modification of the amplitude, so that the amplitude of the mode gets weaker upon propagation, and then we have a phase factor. The phase factor here depends on the beam waist with respect to the wavefront curvature, and then this is a kind of like there's no imaginary unit, so this is still again affecting the amplitude of the wave, and then we have the imaginary phases here, so imaginary terms here. So basically these are the guys telling us how the phase evolution takes place for this mode. And please note here that we do have this kind of extra term here, GUI phase shift, so-called geometric phase affecting the phase when we are going through the focus and then defocusing the beam again. So this is sometimes the kind of important piece of physics explaining what actually happens when the mode is propagating. Oops, sorry. Yep. So let's get forward, and then please note that this is the fundamental mode. So of course the mode distributions of higher order modes would look different, but the Wikipedia will tell you how these modes will look like. So if you ever need to be dealing with that kind of mathematics, you can readily go into the internet and you can find the right kind of mathematics for you. Verification and generalization of this kind of math can be left as a homework problem. I'm not sure if I will be asking from you this year, but at least I guess it could be a nice like a homework. So please be warned. But let's see if I will do it this year. And let's next discuss the general properties of higher order modes. So we have now done the math for the fundamental mode, but of course we can have higher order modes as long as the given cavity symmetry so allows. And it's really the cavity symmetry that dictates how the higher order modes are being formed. So basically it dictates what kind of higher order mode families are being generated. So if we have a Cartesian symmetry within our cavity, what kind of modes we get out? They are known as so-called Hermite Gaussian modes. And if we have cylindrical symmetry, for example, we have a fiber laser, then we are having Laguerre Gaussian modes arising. And what kind of mode distributions they actually look like? Hopefully this helps out for you to slightly grasp that the fundamental mode in both cases looks identical. But when we go to these higher order modes, we start having a slightly different kind of mode distributions. So in the Hermite Gaussian case, we have Cartesian symmetry. So we have symmetry with respect to the x-axis or y-axis. So you can see that for example, here, we can kind of imagine that there are some kind of like symmetry planes with respect to the x-plane and y-plane. And for a Laguerre Gaussian case, it's really more about the cylindrical symmetry. So here, these colors, basically they mean phase of a field. So positive means red and blue means negative. So this is how the phase evolution takes place. And for a Laguerre Gaussian, there is a kind of like continuous phase evolution with respect to the polar angle. So the color scheme here maybe looks a little bit weird. So if you really want to kind of understand how the transverse phase looks like for a Laguerre Gaussian mode, I really recommend that you look into the Wikipedia how these kind of Laguerre Gaussian modes look like, and you can see that there is this kind of like exponent I phi phase term that explains how the mode actually like rotates and how it can even rotate more quickly when we go into higher order modes and so forth. And then going into higher order Laguerre Gaussian modes, we may start having multiple rings, giving rise to kind of like different kinds of modes. So this is how the higher order modes look like, and we don't really go more into the mathematical description. We just wanted to show you that these kind of modes exist, and sometimes we need to be battling against these kind of modes so that we can really deal with the kind of like only single mode lasing and so forth. That's usually the case, that we only want to have a single mode lasing with our laser resonator. So we have free space propagation of a Gaussian beam that fulfills this equation that we just we're writing out. So this is how we can use to understand beam propagation. But the trouble here is that the propagation of laser beams inside laser resonators, often we really need to also understand propagation through lenses, polarizers, or reflection due to the curved mirrors. So basically, this math tells us free space propagation as said here. But in practice, we want to really understand how the laser beam propagates through lenses, how the propagation gets modified, how polarizers affect the propagation, and how reflection from a mirror affects the propagation. So we need to somehow generalize our treatment. And the absolutely nice thing here is that since we are dealing with the Gaussian beams, and they are paraxial beams, so basically there's a correspondence between a single paraxial ray, a single geometrical ray, and a Gaussian beam, we can really describe the propagation and the modification of these Gaussian beams through various optical components using ABCD matrices we have already stumbled upon. And this is absolutely beautiful thing because this can really help out dealing with the mathematics. So interestingly, this is exactly the case so that the propagation of Gaussian beams can really be treated using ABCD matrices. We don't go into the full a derivation how this works out, but we just state that this is indeed the case, and this is a beautiful result of mathematics that we can really describe propagation of a Gaussian beam through a more arbitrary component using ABCD matrices. The key here is that we really need to be treating the Q parameter, and that will be our kind of input vector and the output vector. So optical systems, we can really be treated using matrices as before, same kind of ABCD matrices. And now the Gaussian beam is being treated using a complex parameter Q. And the input Q parameter will be the Q input, and the output will be Q output. And the transformation of the complex valued beam parameter Q given by the propagation through this optical system, let it be a lens, let it be a mirror, let it be a free space propagation within a medium of index n, we can really describe by using these kind of ABCD calculations. And this is absolutely beautiful because we can now calculate the profile of the output beam using pretty simple piece of mathematics. And finally, let's note that if we really need to do these kind of calculations, they are dramatically simplified if we know the position of the beam waist. So this is basically where we are ending up with this lecture, and I will remind you that in the beginning we were also giving you an equation with respect to the inverse of the Q parameter. So from there you hopefully can start grasping why we can really dramatically simplify things when we are knowing the position of the beam waist, where the radius of curvature comes to infinitely large. So here I will thank you for listening my monologue and mumbling about the eigenmodes of optical resonators. This is really cool stuff, really useful mathematics, so I hope you paid attention, and please, I would love to discuss you more during the upcoming discussion exercises about this piece of mathematics. So I thank you for following, and please stay tuned with me when we are soon going to the final lecture of our chapter 3. So chapter 3, so that would be the photon lifetime and cavity Q factor considerations. Thanks and bye-bye.